All right, guys, thanks for watching this video. I want to do a conceptual overview of Chapter 11 because um, we haven't done so many of those lately, but I'd like to make some conceptual videos, but make them shorter and more to the point. So that way, when you get started on the homework, maybe you already have started the homework, you have some idea. There's a lot of problem-solving videos in the module for Chapter 11, so definitely check those out. I'm gonna do some too, but also there were some from Pearson. I think they're pretty good. Um, they do some cool experiments in Pearson, and I really like that. That's why I have that video. Why I have those videos there. Okay, so now we're gonna start talking about energy and its different forms. Okay, we've talked a lot about potential and kinetic energy. You had a bunch of homework about that. We saw that kinetic energy is basically the energy of something that's moving. Okay. If you have moving and has kinetic energy, we also have things like potential energy. Okay. So if I put this on my head, all right, it's going to have potential energy. And if it falls off, that potential energy became kinetic. But there's a lot of other forms of energy out there. Okay, living creatures, we eat food, which gives us all of our energy, and we convert that energy into other forms, motion and potential energy. Um, and so all of those different things are important. We're going to talk about heat, the transfer of energy from one place to another. We're going to talk about how energy flows from a hot thing to a cold thing. And I'll tell you why I don't believe in temperature. Well, I do actually. It's actually a physics thing. But when my wife and I were dating, she always was like, I'm cold. And I'd be like, well, I don't believe in temperature. There's not really a thing of temperature. It's just really the flow of energy from one place to another. So if you have a hot thing, heat flows, energy gets transferred to the cold thing, right? They come to equilibrium, right? It's like if you put ice on your face, you can feel the energy flowing out of your face uh into into the ice cube. All right, so we're going to talk a lot about energy. These videos are really good. I highly suggest watching them. I've posted a lot of these videos in the module. I think they're really good. They have a lot of experiments. I don't have a heat vision camera. I wish I had that, but man, they look at what it looks like in heat vision. I've never had that. I really need to get one of those. All right. So we're going to learn about the practical transfer of energy. So in living beings, we're talking about changing chemical energy into things like kinetic and potential energy. These kangaroos, right? Kangaroos eat plants and they convert that energy um, into kinetic energy and then they jump around because that's what kangaroos do. Pokemon, as far as I can tell, don't actually eat anything, okay? And yet they get all of this energy. Where are they getting all the energy? Where does Pikachu get the energy from the lightning bolts? It doesn't, I mean, what does Pikachu even eat? They never show him eating, at least that I know of, okay? It's also why we don't have superheroes, right? If you move something with a force, I guess with your mind or whatever, it would still take energy in order to do that because conservation of energy must be true. So, that's probably why superheroes don't exist. If you click on these links, they're videos of how to solve these problems, and they're pretty good. I don't know if they're as good as mine. Probably better. I like my videos. Okay. But that I like the guy with the long hair. I think he's from Boulder. He's a cool guy. Okay. So looking ahead, energy use in the body. How does your body use energy? Well, when you eat food, you can convert that energy into kinetic energy, moving. You can run or ride a bike. But when you do that, okay, you're going to lose a lot of energy. In fact, most of the energy from that food goes into creating heat. Human beings are about 25% efficient. And you know this if you work out or you exercise or play sports. As you exert a lot of energy, you get really, really hot. And that's the thermal energy that is from your food. It's heat that's being lost, energy being transferred to the environment. And there, according to the laws of thermodynamics, you can only have an engine that is so efficient. There's certain things that you can't go beyond. So when we burn coal or gasoline, there is a maximum efficiency that we can achieve. And if we have a heat engine, right, you're going to lose a lot of that energy in the form of heat. It's dissipated into the environment when you exercise, right? Your body gets hot, that heat radiates. It's the same thing if you burn coal or gasoline or natural gas to make electricity, or in your car if you're driving a gas-powered car. Most of that energy is just dissipated into the environment, okay? So this is a cool picture. See, here's a teapot, okay? You are heating the water, you're boiling it. There's a phase change. It takes energy to change water from a liquid into a gas. Okay, that takes heat. You have to put energy from the electricity into the water. Okay, but a lot of that heat is lost. It's in a teapot, it's radiated off into the environment. So it's kind of an inefficient process, right? Your water heater, right? We as as civilized people, we always expect there's going to be hot water. So we have hot water heaters in our basement. Um, there's different kinds of water heaters you can have. Some people have electric and some people have natural gas, right? Those are both options that make sense in different things. If you have solar panels, it makes sense to have an electric water heater because you can use electricity to heat it. Um, Back in the 1980s when Jimmy Carter was president, my dad had solar panels that had glycol in it. Okay, so it'd take basically antifreeze, it would go to the roof. There were solar panels there that were black. The liquid would flow through there. It would get really hot from this black box from the sun, and then it would flow down in the water. You could boil water. Okay. And that was basically free. You just needed a little bit of electricity to pump the glycol through the solar panels. Okay. So, depending on if you're clever or not, right, there's lots of ways that you can transfer heat. Natural gas, a lot of water heaters are natural gas because when you burn the natural gas in your house, right, almost all of the heat can be used to heat water. If you have a very efficient water heater, you can capture 90% of that energy. Okay. If you have an electric water heater and you're burning coal, right, the the most efficient that coal plant could be is about 26%, maybe 27. Okay. And so 75% of that energy is lost. So it makes much more sense to burn the natural gas in your house and get that heat directly, right? It doesn't make any sense to basically burn something, create heat, change it to electricity, and then change it back to heat. Every time you convert forms to a different type of heat or you're doing these transition is very inefficient, okay? Someday you're probably going to own your own house and you're going to have student loans and you're like, when I have to get a new water heater, do I want an energy efficient one? Yes, you do because it's going to save you money. Do you want insulation in your house so your house doesn't require as much air conditioning and cooling? Absolutely. It can cut your electricity bill in half or to a third. Okay. If you have bad insulation in your house and you have a crappy air conditioner, okay, and you have a really old furnace, okay, your electricity bill could be $350 to $450 a month, okay? And here's another interesting fact that maybe you didn't think about. When you graduate from college, you're going to have student loan payments. That could be $500 a month. Okay, so you're going to be thinking, do I want to get the fuel efficient water heater? Do I want better insulation? Absolutely, because it saves you money, right? Um, I recently had a car that got 20 miles per gallon, right? And it was a cool car. I loved it, but it only takes premium gas. It was really old. It got 22 miles per gallon. So when the time came, I bought a hybrid. It gets like 50. Okay. Gas is, I don't know if you buy premium, it's about $5 a gallon. Okay. So that instead of paying, let's see, if I buy 4 tanks of gas a month, okay, you're talking that you're gonna pay instead of like $200 for gas every month, you're gonna pay like 80. Okay. Save money. That's one of the benefits of being energy efficient. You save a lot of money. All right, who doesn't like money? If you like money, you want to have energy efficient stuff. All right, heat engine is a device such as a geothermal power plant. This takes energy from the ground, right? Thermal energy in the ground uses it to do work. Okay, you can take uh, energy from the wind through a windmill, solar panels, right? This is energy that's there and you can use it to do useful work. You don't need to burn coal, right? There's lots of ways you can get electricity. There's energy all around us. Okay. Let's see. Now I'm gonna talk fast. Starting to go off on tangents. This video is gonna be, we're gonna go for 15 minutes. I think I've been talking for five. We gotta move along faster. Okay, here we go. Starting a timer. 'Cause, when you get to be an old physicist, you start to talk. All right, but let's get to the point. All right, here's our basic energy model. Okay. If you have a closed system, right, that means that energy can't get into or out of your system. It's in the system. Okay. It can only be in the form of chemical energy, meaning maybe you're going to burn wood to power your steam engine. Okay. Maybe you have food that you can eat. All right. Or maybe some wood that you can burn to make a fire. Okay. You can convert that chemical energy like gasoline, can convert it into kinetic energy to drive your car. Okay. You can run an electrical generator to store the energy in a battery. That's potential. Okay. And then you also get thermal energy as a result of using the chemical energy. You're going to create thermal energy, right? When you change potential into kinetic energy, there's going to be friction, there's going to be wind resistance. So you're going to have thermal energy that's given off. All right. Christina throws a javelin into the air. She propels it forward from rest. She does 270 joules of work on it. Its highest point is gravitational potential energy has increased by 70 joules. What is the javelin's kinetic energy? Well, okay. Let's see. As she propels it forward from rest, okay, she does 270 joules of work on it. So I guess she throws it up. Okay. At its highest point, its gravitational potential energy has increased by 70 joules. All right. So if all of the energy, so she throws it up in an arc. Let's draw a picture real quick. I don't know if I can keep it under 20 minutes. I gotta go faster, but I want to draw pictures. Okay. So the correct answer is 200 joules. That energy changes from kinetic to potential energy. Hey, let's look at another one real quick. All right, reading questions. Typical efficiency of a human body is about 10% is a little bit low. 50% would be um we're not anywhere near 50%. We are somewhat inefficient, so it's really about 25%. Okay, machine uses 100 joules of electric energy to raise a heavy mass, increasing its potential energy by 300 joules. what is the efficiency of this process? Okay, well, you basically take the energy that did useful work and you divide it by the total energy, and that gives you efficiency. So 300 divided by 1,000, that's going to give us 30%. Okay, so how does that work? All right, if we're thinking about efficiency, okay, so our efficiency um, is going to equal useful work divided by total energy spent times 100%. Okay, so we have to multiply it um, here in order to change it into a percentage. Okay, so if we had 300 joules to give something that much potential, the total energy it took to operate the motor was 1,000 joules. Then we multiply this by 100 to change it into percentage. So we cancel our zeros here. These zeros go away, so that gives us zero point 0.3. Then so we have zero point 0.3, the joules cancel, and then times 100. Oh, yeah, times 100. Okay, so that is going to give us 30%. That's how you do it. All right. All right. When the temperature of an ideal gas is increased, which of the following also increased? Okay. Well, I don't know if you've ever boiled a pot of water with a lid on it, or maybe you have a pressure cooker. Okay. But as you increase the temperature of the gas, the pressure also increases. That comes from kinetic energy. As you get gas hot, the gas molecules start moving around much, much faster. They're going all over the place. So, when the temperature of an ideal gas is increased, which of the following also increases? The average kinetic energy, not potential. Mass, that doesn't ever change, right? The mass of the gas is always the same. You can't change something's mass. The number of gas atoms, no, you don't get extra gas, right? The number of atoms in a container is fixed. So it's the average kinetic energy, also the thermal energy of the gas. That's true because um, yes. So when the temperature of the ideal gas is increased, which of the following also increases? Okay. Well, if you increase the temperature, that means that the thermal energy is increasing, and you're also increasing the kinetic energy of the gas, right? When gas molecules heat up, they start moving much, much faster, okay? Um, it doesn't have any more potential. I don't know what that would be. Maybe that would mean you store it in a cylinder, but no. The mass of the gas atoms, mass never changes, and neither does the number of atoms in the gas. Okay, let's talk about um, batteries. Batteries are a great way to store energy, right? You can create an electric potential. Okay, and let's talk about electric cars a little bit. Okay, um, basically, when you drive an electric car, if you have a hybrid like I do, when you step on the gas, okay, you can change some of that energy, your kinetic energy, back into chemical energy in the battery, right? Using a magnet in the brakes. Okay, there's like a coil in there. It's a really ingenious system, but it creates an electrical current. Okay, and then they use that to charge your battery. Okay, so it's kind of an inefficient process, but at least you get some of that energy back. Okay, so in an electric cars are much more efficient. Um, but here's the thing about electric cars. It depends on how you're charging them. Okay. Are they better for the environment? Um, it depends on where you get the electricity. If you are charging your electric car from windmills and a solar panel, yes, it's more efficient. If you are burning coal to charge your electric vehicle, that is less efficient. That is worse from the environment. You'd be better off just burning gas. Okay. So, in a way, hybrids are ideal. Now, if you had solar panels on your house, that's even better, right? You don't need fossil fuels. Okay. Most people don't have that. So right now, probably the best solution is a hybrid. You use gas, it's very efficient. You um, cut down on that because if we make all of our electricity from burning fossil fuels, then it doesn't really matter if you're burning it in your car or you're burning it in an electrical plant. If you burn it in an electrical plant, you lose energy along the way. Okay, so um, unless you have a hybrid. Hybrids are much more efficient than gas cars, and so they take less energy to operate, right? Um, so if you go through this calculation, what you find is, okay, if we compute the energy stored in gasoline, the big takeaway from this is, and I'm just going through this quickly, okay, is that basically, um, the end result of this is that electric cars are 90% efficient. Gasoline powered cars are 20% efficient. So at the time of this presentation, batteries were much worse. They hadn't developed modern electric cars, right? This has come about just in the past 5 years, right? We went from very bad batteries, right? So they could only hold 103 megajoules of energy compared to 348 megajoules of energy. Okay, meaning um, back then you couldn't drive that far in an electric car. Now you can. The batteries last much longer. You can drive hundreds of miles. You do have to go to a charging station. Okay, so the question is, which is better for the environment? Well, um, you're going to pay less money if you have an electric car. Okay, so your fuel costs will be lower. You're going to pay a little bit more upfront. They're more expensive. Um, and you also have to deal with charging stations. They're somewhat hard to find. They're becoming better. Okay, but it also takes energy to create the battery, right? So if you take that into account, you don't start saving overall energy until a few years after you own the electric car because you got to pay the energy to create the battery for your electric car. Okay. But after 8 years, after maybe 6 years, you start to save money or you start to save energy. Actually, if you buy an electric car, you start to save money right away. Okay. So, um, electric cars are getting better. Um, if we had better batteries, right? If all we could save the energy from hydroelectric dams, we could we would have all the energy that we need. Okay, so the real problem is just we don't have good enough batteries. We need better batteries that don't require minerals from China, and we don't use child labor to get the minerals for the battery. Okay, um, let's talk about um, a refrigerator. Okay, a refrigerator is a heat pump. Okay, let's talk about what a heat pump does. Okay, so a refrigerator is an example of, yes, it is a heat pump. Basically, it takes heat from one place and it moves it somewhere else. And it takes energy to do that. Okay, so um, and here's something to think about. Okay, ask yourself this. Can you cool your house by opening the refrigerator door? Would the temperature of your house go down or would it increase? Take a minute and think about that. Okay. I'm going to draw a little bit of a picture here. Right. Um, and then I will leave you with this thoughts. Okay. So refrigerator kind of works like this. Okay. Um, It basically, okay, let's say here's the inside of your refrigerator, okay? Um, and what it does is your refrigerator pumps heat out of this little area here, okay? So it removes heat from, so heat flows this way. This is the inside of your refrigerator, okay? But, right, that costs you energy, right? It takes you, um, you have to do work in order to do this. Okay, so this is work. Okay, um, so you put in work here. It removes the heat from here. Okay, and the temperature decreases inside of here. Okay, but where does this heat go that you take out of your refrigerator? Because what you're doing is you're taking energy inside of here. You're taking thermal energy. Okay, so this is thermal energy, right? And you pump that thermal energy out this way. Okay, where does the heat go? Where does that energy go? It goes into the room, right? Um, And so that energy now, okay, um, so in the room, right, the temperature increases, right? So the answer is if you open the door on your refrigerator definitely can't cool that entire room, okay? But it's gonna make it hotter because you're just pumping the heat into the room. And if it's in the same place, um, then you're not gonna really accomplish anything. Let's talk about the your house, right? You turn on the air conditioner. In Missouri, everybody likes to have an air conditioner because it gets really hot in the summertime. Okay. So basically you have your unit in here that blows cool air into your house. Okay. And always have a unit outside of your house here. Okay. And this is hooked up, let's say, of course, to the nuclear power plant. Here's our nuclear power plant. Right, let's draw a little green radiation symbol here. Okay. So we get electricity, right? It goes along the line this way into your cooling unit. Okay, so this is electrical energy, right? Or power, right? It goes into this unit here. Okay, so what happens? Well, using a let's draw this is hooked up to the blower here, okay? And so what happens? Well, um, essentially, heat flows out this way from your house, okay? Through these little cooling lines here, right? It sucks heat this way, so heat flows out of your house, okay? And where does that heat go once it gets to this unit? Well, the heat goes here to the environment, right? So heat flows from your air conditioner outside, okay? And the heat comes in here. This thing is sucking uh hot air from your house into here, and it blows out cold air. See, this part's cold. Cold air. Cold air. It sucks in hot air. Hot goes in here, right? Energy goes in here. This little cooling thing, right? It sucks heat out of the air. The heat goes to the blower outside of your house and it shoots it off into the environment. Now, interestingly, when you boil water, you're also giving off heat over here at the nuclear power plant too, right? Don't forget about that heat. Okay? Um, right? This is, 75% of the energy is lost at the nuclear reactor. Okay? And here, right, you get 20% of that energy from the nuclear reactor, and then you also lose some energy along the way. You lose about 5% of your power in power lines. Okay? So, 20% of that energy goes to running your air conditioner, right? You pull heat from your house and you blow it out this way. So hot air goes into your house, okay? But here's the thing, okay? The worse your insulation is in your house, okay? Maybe you have bad windows. Maybe you have bad doors. You don't have insulation in your house. Okay. If you have bad insulation, here's what happens. Okay. Well, in the summertime, when the sun is shining, you have a nice black roof. Okay. Because everybody has black roofs here. Guess what? Heat flows into your house through the roof. Okay. Heat flows in this way. Okay, so heat is getting dumped into your house. Okay, why? Because the sun. Here's Mr. Sun. Mr. Sun is shining. He's so shiny. Right? Mr. Sun is over here. Mr. Sun is shining. Let's give him some cool glasses, man. Hey, Mr. Sun, you're so cool, bro. You're so cool. In the summertime, you're so cool. Let's give him a smiley face. He's like, I am cool, man, but I'm hot. I'm so cool that I'm hot. The sun is really hot. Hey, and he shines on your house, okay? That heat flows into your house. It goes down into your house from the attic because you don't have insulation. Because you just graduated from college and you buy a really cheap house. There's no insulation up here. That heat comes into your house, man. And then you have to pump it out here. You're like, hey, man, throw in a nuclear fuel rod, right? We need more energy. Okay. And this is great because it doesn't produce any carbon at all. Okay. And for about 5 years, everything's good, right? Except you have these little nuclear fuel rods. You put two together and then it boils water and it makes steam. Okay. But then after a while, well, those nuclear fuel rods, they run out of fuel. And so the power company's like, hey, man, can we bury these nuclear fuel rods below your house? You don't mind, do you? So now you got some nuclear fuel rods here below your house. Well, there's a little bit of radiation, but it's not much because they buried it in a stable geological formation below your house. I mean, what's the alternative, right? Maybe. Hey, here's your house. Okay, maybe you want to live next to the coal power plant, right? Here's the coal power plant, man. Okay, and here's your house, right? You could live next door to it. Okay, right? Maybe the high voltage lines they go right over your house. Okay, here's the high voltage line coming from the power plant. Yeah, high voltage. Yeah, got a high voltage line here, man. You got electrical cables going in this way. They go right over your house. Guess what? You realize if you get a halogen light bulb, you don't even need to plug it in. You know why not? Right? Because there's electromagnetic radiation coming across these lines, an oscillating electric field, and guess what? Your light bulb can turn on now because that electromagnetic flux turns on the light bulb without even connecting it to an electrical cable. This is actually true. I tried it with the Tesla coil. And since you live next to the coal plant, because who doesn't love coal? Coal's the future, baby. Guess what this is? It's called smog. You like smog? There used to be a lot more smog in the 1980s. You know why? Because there were no regulations for what electrical companies could emit, and so it's like this gray sort of haze everywhere. Sometimes in St. Louis we get a little smog. So uh, now everything's coal. You got the power lines coming in here. You got electromagnetic flux. Got a little bit of smog here. Sometimes you cough when you go outside. Well, anyways, some things to think about when you buy a car or you decide, how do I want to get electricity to my house? Stuff to consider. What I do know is that most people like money. I mean, I like money. You'll like money too. And saving electricity saves you money. Getting a car that gets better gas mileage costs less money. Sadly, you're going to have to pay back your student loans someday, and that money will become a lot more real then. So, that's all for now. Have a great night.
Thank you. Like and subscribe down below.